Maybe from the 1 through 16 stuff, Blake?
Can you do number 15?
I mean, I sure hope I can. It's be a bad day for Mr. Kulik. All right. 15 says the population P in millions of people of Ohio T years after 1990 can be modeled by the equation yada, yada, yada. Based on the above equation, when was the population of Ohio 10 million? Oh, okay. So this, your likely problem is your reading of the question. So it says the population P in millions of people. So when I type in 10 million in here, I'm typing 10. And when I do this guy, everything looks like it normally would. Again, the question said P is in millions of people, so that's how I knew that I had to do it that way. Which, again, like, trips almost everybody up. Oh, Boise, what's that question mark doing in there? That's a weird thing. All right. Oh, that should be a negative. There we go. All right. Reset our window, 0 to 100. That seems fine. Well, let's do 15 to 0. Yeah, that seems good. I mean, the upper bound is really 12.79, but like, I'm just going to use 15 because it's a rounder number or whatever. Oops, scale should be 1. Should be fine. All right, let's take a look. Here's my 10 million line. There's my logistic curve. There's my intersection, second trace, intersect command, enter, enter, enter. 67.67 or 69.67. So let's be real careful here. When was the population? Okay. So you'd say, you know, like between 1969 and 1970 or something, or 69.67 years after 1990 or 1900. You know, something like that would be. You'd put 10 million in instead of, yeah, and it's like 0.02 or something, and just like, oh, Boise, that's a, oh, it never got there.
Nope, never.
Yeah, never got there. Yeah. You're like, what is going on? Yeah. So, it's okay. It's the kind of mistake where it's like, once you point it out, it's like, oh, that's definitely what I did. Everybody does that. It's okay. Others from the homeworks. Okay. So I think then we are on to section 2. In section 2, we're going to be looking at some exponential and logistic modeling. That sounds right. So we're going to start by introducing to you the exponential population model. All right. So our population model here, P of t equals P naught times 1 plus r over t to the t, where P of t is the population at some time t, P naught is our initial population, r is our rate of change as a percentage, and t is a time, and the unit for that time should match the unit on the rate. So like if the rate is per year or something, then the time would need to be in years. The rate was per day, then the time would need to be in days or whatever. Or you'd have to make some kind of adjustment to account for that. So if we think about this population model as an exponential, just as a general exponential equation.
What was that, 1 plus r over 100?
1 plus r over 100. Yes. Correct. Not t. That 1 plus r over 100 is like our b, right? Everybody kind of sees that? And we have like so that piece is going to tell us whether the exponential function we're dealing with is growth or decay, right? The 1 plus r over 100 part. Oops.
Self-defense is usually you have to prove that you were in a situation where like because you are no longer defending yourself. Doesn't matter how expensive
Can you, what's the word before rate?
Yeah, no, I can read.
Matches.
Oh, thank you.
Yeah. Yeah. Just that the time unit needs to match
Yes, that makes sense.
the time unit on the rate.
And once that,
Okay. So a little bit, again, I know my penmanship is less than spectacular, especially after a long layoff where I'm not used to writing. So if you can't read it, feel free to ask. No problems. Here we have indicate whether the following population models are growth or decay, and then find the constant rate of growth or decay. So what part do we need to be looking at here to tell if it's growth or decay? Excellent, the base of the exponential. So in the first one, we're looking at the 1.034. In the second one, we're looking at the 0.9867. So 1.038, or how can we tell then if those numbers indicate growth or decay? And then between 0 and 1, then it's decay. And remember, the base of the exponential can never be negative, can't be 0, can't be 1. So that covers all the possibilities then. Everybody agree? So part A, growth or decay? Growth. Part B, growth or decay? Decay. Everybody feel good with how we did that? Just using the definitions, right? All right. The next piece it asks is to find the constant rate of growth or decay. They're basically asking for R, is what that's saying. So, for part A, all I'm going to do is I'm going to take that value for B and set it equal to 1 plus R over 100. And solve for R. Everybody's cool with that? Solve for R, what should we do? Subtract 1 and divide by 100. Everybody cool with that? I didn't write down the steps, but we said them. That was okay? They're kind of mental mathy, right? Subtracting 1 and multiplying by 100 are both, I think I can handle that in my head. If you can't, that's okay. That's what calculators are for and what writing down pencils and paper are for, you know? Do the same thing for part B. So do the same thing here. We get our R is negative 1.33. So what can you say about the value for R and whether it's growth or decay?
It's greater than. Wait, hang on. Oh, it's what was the question again?
The relationship between the value of R and whether the function is growth or decay?
Oh, it's positive. It's growth.
Yeah, that's all. Positive R's are growth, negative R's are decay. Let me close this and look up. Half the time yelling over the room across the hall. We're out shouting each other. You know what I mean? It's like at the lunchroom, how it gets so noisy because just you're trying to talk louder than the table next to you, and then the table next to you is trying to talk louder than you, and then it just turns into like a yelling match. And the lunchroom becomes like 80 decibels really fast because everybody's trying to out-shout everybody else. That's what it felt like here. You know, just trying to have some fun. Like we can make it silly, can't we? Maybe.
Yes.
Yeah. Let's get weird, guys. All right. Let's do another example. Again, if you haven't figured this out by now, like this whole section is going to just be like story problems up the wazoo. So, all right. So determine the population model with an initial value of 15 that increases at a rate of 6% every year. Since it says population model, clearly we should be using this population model that we just quoted earlier. A population model should have a variable for its independent and dependent variables. So those pieces are not going to have anything filled into them on this. What we do need to fill in is a value for P naught and for R. What is our value for P naught going to be? 15, the initial value. And the value for R should be 6, the rate of change. So when we plug this all in, and I simplify the 1 plus 6 over 100, I get that. And I should probably be specific here. And say the unit of time for t. That feel okay to everybody? You guys know just to holler out if I'm doing anything you're not sure about or you didn't like. Okay. Next example. Again, determine the population model with initial value of 15 increasing at a constant rate of 6%. But here, it says every 6 months. So the initial value still 15, the R still 6. What am I going to do here though at t? What unit of t do you want to use?
T over 6.
Okay, so are we going to write t in months or years? Because those seem like the two obvious choices, right?
Can we write it in like 6 months and then just remember to use the factor change language?
I would prefer that we write it in either like years or months. But either one is going to be okay, and we can do it. We'll have to modify things slightly differently each way. But let's make a decision right now which one we want to try first.
Probably years.
Okay. Okay. How many times does 6 months occur into 1 year? Twice. So this should be 2t. Everybody cool with that? So we have 2 of those full rate changes in 1 year. If t is in months, how many rate changes do we have in 1 month?
1/6.
1/6. So I would write t over 6. Either of these is fine. If the direction said to write the model with t in years, then it would the first one, or if it said t in months, it would be the second one, or if it didn't indicate which one you wanted, either would be appropriate. So it just kind of like depends on the directions, I guess, but either of these are appropriate. And I guess you could do days too if you wanted to, but like, who wants to do that? Not me. Everybody feel good on writing these? This is the trickiest piece, is when we like give you like a non-standard length of time or whatever. All right. Let's do another one. And again, if I'm going too fast or you need a minute, holler at me and we can certainly take a minute and slow down, but I'm trying to like do a bit of talking and pausing at places so you're able to kind of think and catch up at the same time or whatever, so it's not like too breakneck. But again, we've been away for 2 weeks and I'm not used to, I get going fast sometimes anyway. So anyways, here we go. Suppose a colony of bacteria, of 120 bacteria, is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So when I read a question like this is really 2 parts. So the first part is going to be writing a model, and then the second part would be solving that model for some specific situation. Does that, everybody feel that when you read it? Okay. Pretty clearly a population situation, because we're talking about, like organisms reproducing. Everybody cool with that? Pretty clear that I'd want to use the population model here. Okay. What is the P naught in this situation? The initial amount, 120. Okay. So then I have my 1 plus R over T, or R over 100. What is the R in this situation? So doubles is giving us the R.
Or no 100, isn't it?
It would be 100, yeah. So like, if you had $2 and your money doubled, you'd have $4, right? What percent change was that? 100%, right? You took 100% of your $2 and added it to the $2. Does that, everybody see how why doubling is 100% there? Again, a lot of this becomes like grammar decoding, so I want to take the time and like walk through why we're able, like why we should say, oh, doubling is 100% change. Okay, and then our T, what unit of time should we write T in? Hours seems appropriate. Okay, so in our case, our rate of change is every 3 hours, so we should write T as T over 3. So then we want to predict how long it'll be to get 400,000 bacteria. Notice that 1 plus 100 over 100 is 2. So there's our doubling. Really obvious that we've done that correctly now, right? And it's calculator time from here. So what did we do? We did the left-hand side, and then we do the right-hand side. Oh, Boise, get rid of all that stuff. Everybody's cool with that setup? The trickiest part is usually getting your windows squared away. So if I think about this real quick, 3 hours I'd have 240. 6 hours I'd have 480. 9 hours I'd have 960. 12 hours I'd have, whatever. It's going to be a long time though, right? To get to 400,000. So I'm going to stick with 100. That's probably appropriate. I don't know. We can always go back and change it if we need to. My Y minimum was really 120, but I'm just going to leave it at 0. My Y max needs to be 400,000 or bigger. I'm going to make it 500,000. So that I can see the line really easily and it's not just like the top of my window or whatever. And then I guess go by 100,000s. Okay, that looks good. Let's hit graph. There's my 400,000 line. Here's my population curve. Whoa, that happened faster than I thought. Doubling is super fast, guys. Second, trace, intersect command. Since I have only 2 curves and 1 intersection, I just press enter 3 times. So 35.11 minutes. Nope. Hours. And that's the advantage of doing this is like where T is in hours versus like T is every 3 hours, then we don't have to muck around with like altering our answer, right, Jillian? By doing like T over 3 is just our answer is our answer.
Yeah.
Instead of like, you could do it what you described, it just becomes like kind of a hassle.
I just want
I just want to make sure that like when we actually do one of these problems, point out to like why that's helpful. Alex.
Can I go to the bathroom?
Absolutely. All right. Another specific population situation is radioactive decay. Do you guys talk about radioactive decay in your chemistry classes anymore? Do you remember talking about this? Like for a half a minute? Well, it's really easy. Well, it's going to be really easy for us because we have better mathematics tools. And we're not worried about like the different types of radioactive decay. All right. So what the idea here is you have some specific element or even, I guess, compound. Maybe I should be a little bit more vague. And over time, that compound is going to lose subatomic particles and turn into a different substance, right? The rate at which that happens is called your half-life. That's the amount of time that it takes for half of the original sample of your material to degrade into something else. Okay, with that idea, the key here, half-life implies that the R is going to be if you go to a store and there's a sale for half off, what percent? 50% off, and the off part would imply that it's actually what? Negative 50%, yes. Because it's coming off rather than being added on. Everybody's cool with that? So whenever you read half-life, the R is just negative 50%, and we can do this just the same as we would our population model. So let's look at a couple of examples. All right. Suppose that the half-life of a certain radioactive substance is 35 days and that you have 10 grams of substance initially. Find the time it would take for there to be only 1 gram remaining. As we saw in the previous example, I'm really going to think about this as 2 questions. First question is writing the model. The second question is going to be solving that model for some specific value. Does everybody kind of see that same thing? All right. So we'll start by writing our model. The initial value for this is 10. Very good. And the R is going to be negative 50. Whenever it's a half-life, the R is always negative 50. And then the T, what unit of time do we want to use for this? I would do days. So here it should be what in the exponent? How many half-lives are going to occur in 1 day? Or how much of a half-life can occur in 1 day? Takes 35 days to get 1 half-life, right? How much of a half-life do we get in 1 day? 1/35. So this should be t over 35. It's usually very easy to think about whether it's division or multiplication just because of, like, can I do a whole thing or less than one, full change? And if it's less than one, it's division. If it's more than one, it'll be multiplication, Everybody's happy with the first part, so that's like our yellow. For the blue part, what am I plugging in? I have to plug in something to either P of t or t to solve, right? I'm plugging 1 into P of t, yeah. And notice again that if I simplify 1 plus negative 50 over 100, that's a half. Half-life. Okay. So 1, and then 10 times 0.5 to the x over 35. And then set our window. Usually this is the trickiest piece. If I think about this, so after 35 days I have 5 grams, then 70 days it's 2.5, and then 105 days it's like 1 1/4. So it's going to be more than 100, right? And then after 1 1/4, another 100 or 35 days gets me to 140, and it'll be less than a 1. So 150 should be plenty. And then 0 is going to be the minimum. Since it's a decay, the least amount of stuff you can ever have left is nothing. And then we start at 10, so let's just start at 10. You know what I mean, guys? So there's my 1 gram left. There's my decay curve. There's my intersection that I'm looking for. Yay! Second trace. Intersect, enter, enter, enter. 116.27-ish days. Oh. Everybody feel okay on that? Any different than the previous examples? Not really, just a little bit of like vocabulary or whatever, but we didn't do anything different mathematically. Anise? Sure. And then remember last time we talked about exponential and logistic functions. And one of the things we talked about was specifically when we talk about populations, that the logistic model is probably a little bit more realistic of a model because we have that built-in like upper bound or whatever for it. So we can ask kind of the same sorts of questions using a logistic function. Notice in this problem, the logistic function is given to you. You don't have to construct your own. That would always be the case. Oops. All right. You start a bunny petting zoo. Look at you, an entrepreneur. You determine the population of bunnies on your farm can be modeled by the equation B of t equals 800 plus 99 e to the negative 0.5 t, where t is measured in years. How many bunnies do you have initially? What is the maximum sustainable population of bunnies on your farm? And then how long will it take for you to have 500 bunnies? I'd like to ask one additional question before this. Is this, looking at the logistic function, is this growth or decay? This is growth. So remember, there's two types of these logistics. I think we use C there. Right, where they looked like these were the two different types of logistics. For this one, so what we're looking at here, since we have the version with E in it, our B value is 0.5. So this is growth. Which would make sense from the question, right? We're talking about a population of bunnies. Probably talking about growth. You know, is that okay with everybody? Again, this was recapped from section 1. I just figured it happened before break, so let's just touch on it again. You know, we didn't talk about logistics last year. It's worth coming back and just taking one more pass at it. Okay, for our specific problem here, it says, how many bunnies do you have initially? What time does initially imply? 0. So all I'm going to do is B of 0. Okay, so negative 0.5 times 0 is 0. E to the 0 is 1. 99 times 1 is 99. 1 plus 99 is 100. 800 divided by 100 is 8. Or you could type that into your calculator if you didn't want to mental math it. We had 8 bunnies to start. 8 little bunnies. Everybody cool with that? Part B, the maximum sustainable population is really just like, we're talking about the upper bound for the function. For logistic function, does everybody do you remember the upper bound? It has an upper bound and lower bound. The upper bound is at C, and the lower bound is always 0. So in our case, what's the upper bound? $800, right? So the C is just 800. Well, easy. Again, no mathematics there. I'm just kind of using some definitions. Everybody's okay still? All right. Part C says then, how long will it take for us to have 500 bunnies? How long is asking us to solve for T? Everybody agree with that? So where's the 500 going to be plugged into? B of T. So we have left-hand side, right-hand side. I'm going to use the fraction command here because I don't want to muck around with all the parentheses that I would need to make sure everything is in the fraction the way I want it to be. I did not mean to scoot you over there. I can just use that fraction command and then just type it the way it looks like on my sheet of paper, which is lovely. So I got that typed in. Go change my window here. So no idea how this is going to be doubling, but it seems like 100 years ought to be sufficient. And then we started with 8 bunnies. That's good enough to 0. We're going up to 500. I know the upper bound is at 800, so I'll just set that as the top of my scale, going by 100s. Everybody okay with that? If I have to go back and muck with it a little bit, I can, but I assume 100 years is going to be more than sufficient. There's my 500 bunnies. Whoa, that happened fast. It's almost like bunnies are famous for reproducing quickly. That was a joke, guys. Because there's like a rather not appropriate for the school classroom idiom about bunnies reproducing quickly. I think I dodged that mine well enough there. Yeah. So it took about 10.21 years. You went from 8 bunnies to 500 bunnies. All those bunnies, huh? It's a good thing they're cuddly, right? How many of you, does anybody have Mr. Little right now? You should ask him about his chinchilla farm.
I did ask him.
Oh,
Is it
good.
Chinchilla farm?
Yeah, you guys didn't know that? No. They're really cute. You guys should ask him.
Hard to take care of.
So that would close section 2. We're going to start section 15.3 then, talking about logarithms. Yes! This is what I've been waiting for. I can stop graphing this stupid things on the calculator and do this algebraically.
Yeah. Ooh.
Plus, if you've taken the ACT recently, did the log show up? Yeah, there's quite a bit of them on there. So probably worth, if you think you're taking the ACT again, like, it's good that we're doing this again, right? Yeah, we'll get better at it. All right. So let's start with our definition of a logarithm. So let's say we have some exponential equation. B to the y is equal to x. So I know for an exponential equation that b has to be a positive number not equal to 1, right? That was one of the requirements for our exponentials. Again, that was a before break detail that is an important one, so we're mentioning again. If b is a positive number and I raise it to some power, what does that imply about the answer? A positive number raised to some power, what can I say about the answer to that? Has to be positive. And I would, everybody agree with that? Okay. So if we have some exponential equation, what that implies is, or the way we define a logarithm, we say the log base b of x is equal to y. So these guys come with us as a necessary result. But let's just take a moment and look at this definition and see what it's really saying. So this logarithm is really the answer to an exponential equation, right? So for example, if I say like 2 to what power is equal to 7? Well, the answer to that is 2 to the log base 2 of 7. Should give me 7. So this logarithm is really just an answer to an exponential question. Is that okay? So let's do a couple of examples of just computing some logarithms by hand. And again, mostly this is going to be an excuse to review some properties of exponents, because these are things that we forget but are super important tools to be used in this chapter. So let's say we have log base 4 of 16. We want to figure that out. Without using our calculator, we're going to just do this by hand. So what I'm going to do is I'm going to say, okay, let's say that this is equal to x. If I use my definition of an exponent, or of my the definition of a logarithm, that allows me to write the exponential equation 4 to the x is equal to 16. Oh, so what's x? So that just says log base 4 of 16 is 2. Oh, okay. Easy enough. So let's say we have log base 5 of square root 5. So again, first things first, let's say that's x. We're going to rewrite that as an exponential equation. So 5 to the x is equal to the square root of 5. Good. So we remember that the square root of 5 is 1/2. So x is 1/2. Again, if you've forgotten that, the rule that we use there is the nth root of any number is, or the nth root of x is x to the 1n. As those kind of exponent rules pop up, I'll just recap them a little bit. Okay. So again, log base 3 of 1 over 27, we'll say that's equal to x. So I have 3 to the x equals 1 over 27. Yeah, so good. 27 is 3 to the third. And I remember that the negative exponent makes a reciprocal. So that tells me then x is -3. Still doing okay? Oh, this is a neat one. Log base 12 of 1. Again, we'll say that's x. So if I write this as an exponential, what's the exponential equation I'd write here? (12 to the x equals 1). So what's x have to be here? 0. Yeah, very good. You guys remember your properties of exponents. Remember, any non-zero number to the 0 power is equal to 1. 0 to the 0 is actually indeterminate. We'll call it undefined, but it's not. Sometimes undefined means infinite. Sometimes undefined means like there's multiple answers that seem to be correct. Let's say we have log base 8 of 8. Again, we'll say that's equal to x. Use our definition of logarithms. What do I write? 8 to the x equals 8. So x is 1. We feel okay using that definition of a logarithm to evaluate things. Basically, the idea is just to recast it as an exponential problem, and then it's usually pretty easy. Some takeaways here. So any log of 1 has to equal 0. Again, the reason being that b to the 0 is equal to 1. Why don't I have to worry about b being 0? We defined b as being greater than 0 and not equal to 1. So the possibility of having 0 to the 0 can't even happen. So we can say that strictly always. Everybody cool? How about log base b of b? What's that got to be?
1.
Always 1. Again, that's equivalent of saying b to the first is equal to b. That's a no-dir. Okay. How about this one? Log base b of b to the y. Yep. This is what we saw in the very first example where we had log base 4 of 4 squared was 2. 16 was how we wrote it, but it's 4 squared. So this is basically just saying b to the question mark equals b to the y. And the last one, how about b to the log base b of x? What's that have to equal? Just has to equal x. Again, why? Because if I take the log base b of both sides of this equation, it simplifies down to log base b of x equals log base b of x. So the two that are like ultra important for us are those bottom two. We'll use those super frequently when we start solving exponential equations or logarithmic equations. Those are going to be our two primary tools. So you'll definitely want to make a note of that. So right now we have a whole bunch of logarithms, right? We have log base whatever other than, as long as it's a positive number not equal to 1, possible. Log base 1, not okay. But log base a half, log base 12, log base 17 over 7, log base square root of 32, like any of those things are fine. But there are two special logarithms that we give special symbols for. The first one is called the common logarithm. and that is log base 10. But we don't ever write log base 10 on our paper. We just write log, and we understand that to be log base 10. Just like when we write the square root, we don't write the index of 2 there. We just understand that the index of 2 is there. The other is the natural logarithm. Oops, I forgot the m at the end of that. That's log base e. But again, we don't write log base e. We write ln. You'll notice that when I'm writing my logs, I'm always writing them cursive or script. I do that because the letter L-O-G frequently turns onto students' papers to 10G instead of log. If I write it cursive, I will never do that because it doesn't look like a number anymore. Just like ln looks like 1n, and we start like, oh yeah, just 1 times n is n, and I divide by n or something. Just like terrible, terrible mistakes happen. But if we write it cursive, we won't tend not to make those kinds of mistakes. All right. The nice part about the natural log and the common log is they're built into all of our calculators. So if I wanted to do like, you know, the common log of 7,000, I can just type it onto my calculator. Or if I want to do the natural log of 4.5, I can just type it into my calculator, and it's built in for me. Everybody cool with that? All right. So, there are 3 special properties of logarithms that describe to us how we can add, subtract, and then like 2 logarithms or multiply, you know, a logarithm and a constant together. So the first one is called the product property. And it says that log base b of xy is equal to log base b of x plus log base b of y. And now that seems kind of strange, right? That when we multiply or we add 2 logarithms together and then we multiply the results on the inside like that. What this really is, though, is just the logarithmic version of this property of exponents. That when we multiply 2 exponents with the same base, we add the exponents. Here we're saying that like multiplication outside the exponential turns into addition inside the exponential. And with the logs, we're seeing that multiplication inside the logarithm is turning into addition outside the logarithm. It's just because exponentials and logarithmics are inverses, the property is just reversed, basically. Is that, you guys see that? Okay. The next one is the quotient property. So log base b of x over y is going to be the same as log base b of x minus log base b of y. Again, this is the same as the division property for exponents, right? We see the division outside the exponential turns into subtraction inside the exponential. The reverse is true for the logarithm. Division inside the logarithm turns into subtraction outside the logarithm. Okay, that's seems reasonable. Certainly expected that if multiplication turns into addition, that division would turn into subtraction, right? Like that's much, or not surprising at all. The next one is the power property. So this says log base b of x to the c is equal to c times log base b of x. And this one is related to the, let's use, the exponent of an exponent property. This one's a little harder to see how that property would be directly applicable. But I promise you that that is what's going on there. And the last one is called the change of base formula. And this one says that log base b of c, what did I use here? Oh, well, let's use a, I guess, is equal to log base c of a over log base c of b. Now, this change of base formula was something that, like when Mr. Kulik was a math student, you used the heck out of that thing. You guys will probably never use it. So let me explain to you what happened between when Mr. Kulik was a high school student, when you are now currently high school students. What the logarithm chapter in Mr. Kulik's textbook looked like was, if I wanted to do like log base 2 of 3, I would use the change of base formula, and then I would go to the back of the textbook and find the table of logarithm values and have to look up the common log of 2 and the common log of 3, and then divide those on my 4-function calculator, because even the scientific calculator I had back in the day didn't carry logarithms necessarily. They existed, sure, but they weren't like common practice. So like you were looking stuff up off of a table in the back of your textbook and using the change of base formula to evaluate these. How are you going to do something like log base 2 of 3? What you will do is you'll take your calculator, you'll press the math button, you'll scroll down to the bottom and find the log base command, and you can just simply type in log base 2 of 3 into your calculator and it'll take care of it for you. Which is much nicer than like sifting through tables of values of logarithms to type into a 4-function calculator. I want you to realize like how far like a simple piece of mathematics education has changed with just the availability of, you know, something that has more computing power than probably this computer on the space shuttle that went to the moon. Just like to point that out to you, that like that's how big of an accomplishment going to the moon was. Is that probably the computer on the space shuttle had less processing power than your calculator does, which is wild. All right. So just to illustrate here, let's prove one of these things. Okay, I'm just going to prove one of these properties just so you can kind of get a feel for how something like that would be done. So I'm going to just define, I want to use something different here. I'm going to use that. So I'm going to define these two values. I'm going to say a equals log base b of x, and b is equal to log base b of y. I'm going to convert these into exponentials. Everybody's cool there? I'm going to multiply these two equations together. What's b to the a times b to the b give me? Yep. And then I'll just take log base b of both sides. Oops, wrong b. And then if you remember, I'm going to use this property here, which allows me to just cancel those out, giving me a plus b is equal to log base b of xy. And I defined a as log base b of x and b as log base b of y at the very beginning. And that's the product property. To do the quotient property or the power property, you'd do similar things. You're just using, but the substitution situation would be quite similar. Sydney? Because it's the end of the proof. Like that's the period at the end of the proof. Like if you read a magazine article or something, especially one that spans several pages, that at the very end they put like the filled in box at the end so you know that there's no more article. It's the same thing with a proof. We put the filled in box at the end to indicate the proof is over. That's all.
Did they do that in magazines?
Mm-hmm. Yeah, if you're reading like a Time magazine article or something that spans several pages.
Oh, okay.
You don't read magazines anymore.
I don't read fancy magazines.
Well, I mean, they're not really fancy magazines even. Like trash magazines do the same thing too.
Really?
Like Rolling Stone or what? I not that that's a trash magazine, but it's not like, you know, it's not like it's the New Yorker or something, right? All right. So we need to stop here. This feels like where we should stop. Next time we'll talk about what we can use these these sets of properties to do. There's two types of problems. You guys should be able to do up through 70.
Oh.
Well, in fairness, there's like, 10 problems in there that are like literally just type this into your calculator and press enter.
Exactly.
And then 20 of them
It's
straight up
pretty
just
great.
mental.
Yes, and then like 20 of them are like those mental math problems that we did at the beginning where you're evaluating the log without your calculator that are like, it's not really very hard.
Don't worry.
Okay. I know you will.
I
Especially since you figured out the millions thing on question 15.
The what?
The millions thing on question
Yeah,
15.
holy crap. I spent more time than I'd like to admit on trying to figure out what
Like, what is going on with this? I'm doing it the right way. And it's,
Exactly.